mechanics. So to understand quantum field theory, you need to know Dirac's relativistic quantum mechanics, and to do that, of course, you need to know quantum mechanics and special relativity. So yet again, special relativity, very important. All right, okay, so that's the tangent finished. So back to the first problem. So you're asked to find the difference in wavelengths before the collision and after of your photon. So you're asked to find this difference in wavelength is equal to this amount. And you assume both conservation of energy and momentum. All right, well, let's start with conservation of energy. Now, probably the most famous formula in all of physics from the general public's point of view is E equals mc squared, Einstein's famous formula. Well, here it is here. So this stationary electron here still has energy, right? It's rest energy. The energy it has, just due to its mass, is m naught, and the rest energy of this electron will be m naught. The naught here just talks about its velocity. Well, its velocity is 0, it's not moving. Okay? So its rest energy will be m naught c squared. So that's where this term comes from. So you have the energy, we're talking relativity now, right? So if you've not done any special relativity, this might sort of be going over your head. But don't worry too much, because I'll be doing a whole course on special relativity, doing it thoroughly, like every point. This, the French text is how many pages? 250 odd. Yeah, not bad. So we'll be doing it thoroughly, so you'll understand all this stuff. Okay, so the energy before the collision must equal the energy after the collision. That's one of the basic laws of physics. Energy is conserved, meaning it doesn't get lost or added to, it just stays the same. The total energy remains the same. Basic law of physics. All right, so what is the total energy before the collision? Well, you have the energy of the photon coming in, so that's hf1, right? That's its incoming frequency, plus the energy due to the mass of the electron, so that's m naught c squared. So that's the energy before the collision, right here on the left-hand side. Now, what's the energy as the photon bounces back, after the collision? So it has to be the same. Well, it'll have a new frequency, lower, of course, because the energy of this photon must be lower, because the electron now was given a kick. So it now has energy of motion besides its energy of the energy due to its mass. In fact, because it's moving, its mass will increase, right? As you observe it. If you're an observer here and you're looking at what's happening, you'll see this this mass here move off to the right, and with a certain velocity. And because of that velocity, its mass will go up. Now, if you've not done any special relativity, you may be going, huh, at the moment. But that's one of the weird phenomena that comes out of special relativity. As the velocity of a particle gets close to the speed of light, gets close to c, c is just a symbol for the speed of light, its mass really starts to go up, really starts to shoot up. So its mass will go up due to its velocity. Okay, so so now the energy of this moving particle will be mc squared, not m naught, but m. Right? That m is a function of its velocity. As v increases, this m increases. Right? It's one of the 3 or 4 major phenomena that come out of special relativity. Well, let me just give the essence, like in a sentence, of the weird phenomena coming out of special relativity. Imagine I'm here, stationary, and you're in a rocket, let's say, and you just go boom, you just shoot past me at speed v. And I look. Let's say your rocket has a lot of glass, and I can see through the glass and see you, and I can see your clock. and you're shooting past, as I see it, at velocity v, pretty close to the speed of light, I will see your clock tick along more slowly than mine. So I will see your time ticking along at a lower rate than my time. So your time interval will be less than mine, as I see it. I will see the length of your rocket shrink from what you measure it at. So lengths shrink. And I will see the mass of your rocket go up because of its velocity, higher than what it is when the rocket was on the ground and not moving relative to me. Okay, so time goes slower, lengths shrink, as I observe them. It's all relative to who the observer is. Lengths shrink and the masses go up. And from there are three mountains, and from that you can deduce the E equals mc squared. Energy and mass are equivalent. Really basic phenomenon coming out of special relativity. There's a limit to the speed of light. C is the maximum speed. Anything can go. What else comes out of it? That no matter what the speed of the observer is, if I'm traveling, well, if you're in the rocket and you shine out some light from the front of your rocket, and I measure the speed of light, and imagine you're going at half the speed of light. I will not measure the speed of light as I see it at c plus half c. I will not see it as 3/2 times c. No, I'll just measure it at c. So the speed of light is the same for all observers, independently of the speed of the source or the observer. It's all c. Now that's pretty weird, but anyway, that's that's the essence of special relativity. Okay, so the energy after will be the energy of the photon, so that'll be hf2. The frequency will go down because the energy of the photon must go down. Okay, and mc squared, that's the energy due to the mass of the electron and its motions. So mc squared. Okay, so here's concept. This is energy before, energy after. They have to be the same because energy doesn't disappear, gets conserved. The total energy remains the same before and after the collision. So that's equation 1, right? Now conservation of momentum, and remember everything's occurring in one dimension along, let's say, the x-axis. Okay, there's no deflection. The photon doesn't sort of bounce off and then head off like that. It just stays on the x-axis. It simplifies the math. So this is a simplified version of the Compton effect analysis, the derivation of his formula. And so this is a special case of the Compton formula. All right. Okay, conservation of momentum. Now you're talking about momentum, right? Energy is a scalar. Are you familiar with the difference between a scalar and a vector when you're talking physics? I mean, vectors in mathematics, that's something else. Two different languages. I mean, a physics vector is a special case of a general mathematics, pure math vector, but don't worry about it. So, speaking as a physicist now, a vector, what's a vector? What's a scalar? A scalar is just a number, like temperature, energy. A vector is a scalar, so you need to supply a number, but it also has a second property, and that is the direction. So velocity is a vector because you need to know what the speed is, but you also need to know its direction. So for example, if this pen is traveling 10 miles an hour in that direction and 10 miles an hour in that direction, the speeds may be the same, but the velocities are different because the directions are different. Okay? Now momentum is is an example of a vector. Right? So the direction is important. So we need to pay attention to the direction. Okay, so the momentum before and the momentum after the collision remain the same. Momentum also conserved, one of the basic laws of physics, along with energy and others. Okay, so but this time we're talking about momentum, so we need to pay attention to the direction of the momentum. Right? Well, let's say a momentum moving to the right, a momentum in this direction. Let's call that positive, and so any momentum going the other way is negative. Right? So now the momentum of a photon is its energy divided by c. Where does that come from? Special relativity. Well, if you've not done any special relativity, just accept it. Okay. So the momentum of a photon is its energy E, in other words hf, divided by c, the speed of light. Okay. So the momentum this way will be just its energy, so hf1 divided by c. That's the momentum here. There's no momentum here, right? The momentum would be mv, but v's 0, so there's no momentum term due to the electron. Okay, so there's nothing here, plus 0. Now after the collision, the photon bounces back in the opposite direction, so you need a minus here, because momentum is a vector, the direction is important. So the momentum